Okay, good afternoon, everyone.
Good afternoon, sir.
Today we will just, whatever we have done today, for that we will be discussing the exercises and the derived results only, nothing more than that. The consequence of whatever we have defined, we will be studying. There isn't much here. So any questions from the morning class? What we had stated was this one. That is, if you have a Quaternion P plus U sine theta, it's not here. Okay, P plus U sine theta. Sorry, cos theta plus U sine theta. P naught that was. So cos theta plus U sine theta. Then if you use this multiplication in a special way, PQ P star, that is your LP operator, where Q is the three-dimensional vector under consideration in the quaternion form. That is, you have converted a vector into a quaternion. So if you use this PQ P star operation, then you found out that for any arbitrary quaternion P, the vector part of P represents the axis of rotation. That was this proof. That is LP of K times P is K times P itself, vector part of P. And then if you consider a vector which is orthogonal to the axis of rotation, which is N, then we noticed that this vector N did not come out of the plane orthogonal to the axis P. So the interpretation what we gave after multiplication was this one. That is, the N vector was rotated by an angle 2 theta and it became LP of N. So the cos theta plus 2 U sine theta, where this plane represents the one which is perpendicular to U axis. So in this U axis, any vector in this U axis will be rotated by an angle 2 times theta when you multiply it with PQP star. When you multiply
Recording
it,
in progress.
any questions from that morning discussion? This is our interpretation now. So any arbitrary vector you broke into two parts, one along the axis P and another orthogonal to the axis P, which is your N vector. Then after rotation, it became A plus LP of N. LP of N was rotated by an angle 2 times theta with respect to the orthogonal vector N.
No questions.
So this is for one rotation. Suppose if you wish to rotate by two different quaternions, one P and another Q, what should you do? You simply do one rotation first and another rotation next. So that is called as the composition of operators, which is similar to multiplication of matrices, if we have already seen. So in this particular expression, LQ dot LP. So which is the first rotation?
P.
Is with respect to the P. Yes, very good. And then you rotate with respect to Q. R is rotated first by LP and then by LQ. And if you write it as one, see, we had already seen matrix multiplication. By doing matrix multiplication, I can get a single matrix. So similarly, what is the single quaternion which represents the composite rotation?
P.
For that, you notice this quantity. If you expand what is given in the second bullet, you get P R P star. The second one, if you expand, you get Q P R P star multiplied by Q star. So it is P star Q star. And on the left hand side, you have QP and P star Q star. So therefore, in order to express like this, you need a identity which equates QP whole star equals to P star Q star. So once you can do that separately, it is similar to the complex numbers conjugate law. that is A into B whole star is equals to B star A star. Remember that even in the matrices A B whole transpose is B transpose A transpose. So this transposes, star operations, all of these are related in some way. So each of them uh, are related in some way, in the sense they are generalizations of each other. So if you think of transpose as a star operation or star as a transpose operations, we can relate them. In fact, in one of the classes, we had equated these complex numbers to matrices, if you remember. And then when you take the conjugate, what happened? So if it was A, first row was A minus B and
Transpose.
B A, when you transposed it, it became AB and minus BA. You can clearly see that the transpose and the conjugate are related to each other. So that is how these things work. So anyway, we will not go into that, just showing some relations. So now the question is, we had done only P or P star. What is P star or P?
Minus 2 theta.
Excellent. Or you can think of it as in axis is ulta, same angle. Inverse rotation. You are right. One is rotating in one direction, another rotating in another direction, because P star's u vector is actually minus u. Therefore, the rotation is with respect to minus u axis. The angle will be the same angle. So both are same expression. Okay, so let us do some exercises by discussing. Suppose if you wish to rotate a vector in 3 dimension by an axis 111 and angle 2 pi by 3. What is the quaternion corresponding to this? Theta will be how much?
4 pi by 3. Sorry, pi by 3.
Pi by 3. Very good. And the axis will be along 111. But you should carefully choose, because finally we want P naught square plus P1 square plus P2 square plus P3 square equals to 1. So you have to make sure that you carefully choose. So the geometrical interpretation, if you go back and see for this particular rotation about axis 111 by an angle 60 degrees, is that the axis ijk will become jki respectively. Anyway, this you can go back and verify. And which quaternion performs this job? It turns out that this is the one. That is half plus half I plus half j plus half k. So similarly, if you wish to determine a quaternion which rotates by an angle pi by 2 along the k axis, what is the quaternion? Theta will be how much?
Pi by 4.
Pi by 4.
Pi by 4. Very good.
1
One
by
by
root 2 minus 1 by root 2 k.
Yes.
Pi by 4 minus
1 by root 2 minus
1 by root 2 plus or minus 1 by root 2 k.
k, only k axis is there. Yeah. Am I hearing it properly? Plus or minus?
1 by root 2 k. K vector.
So it is, so why plus or minus?
Depending on, yeah, it will be, I'm not sure that it will be plus or minus. So
Yeah, so it will be when, okay, you are saying that it can be either negative rotation or plus. Let us assume only positive sense, so it is plus
the
k.
plus side.
Yes. So similarly, one can write for I-axis rotation. So the combined rotation will be what? Multiply these two expressions. That's all. Okay, it is as simple as that. So you have converted matrix multiplication into quaternion multiplication. So you have converted matrices into algebra, normal complex algebra. So you can go back and work out what is the geometrical interpretation just for your. Suppose you are given A cos theta plus BU sin theta. What is the inverse of this?
A cos
Conjugate divided
plus
by norm. That's all. Okay, conjugate divided by norm. Just not difficult to write that out. And then suppose if Q was A times P. Now this is interesting, where P is a unit quaternion. You can go back and show Q inverse VQ is nothing but P star VP. Why does this happen?
plus Q inverse is just Q star divided by A square.
Yeah, right. Q star divided by something. That is nothing but P star divided by norm of Q. And Q is also A times P.
So the two A's in the numerator will get cancelled.
Right. So actually A is your norm here. Assuming A is a positive quantity, A is behaving like the norm. Even otherwise, the minus can be taken inside the thing. So what do you notice here? What is the conclusion? So star is not compulsory. Inverse can also do the job. Do you recognize that?
Yes, sir.
Yes, sir.
Yeah. So that is, however, the interpretation cos theta and those things you should carefully work out. Those numbers will not be lying less than 1 or something. Therefore, the definition of that cos theta and all will become difficulty. Therefore, it is preferable to use the unit norm versions where the interpretations are easier. But notice that mathematically, inverse will do the job similar to what your unit vectors or star operation can do the job. So this
Sir,
is a major conclusion. Yes.
sir, we're defining inverse in such a way like norm by, P star by norm, or is it like computing from some other expression?
We are not defining, we derived it, no?
Okay, sir.
Okay, how did we derive it? We can see. I'll show you the derivation. This one. We want inverse. This is inverse is simply a symbol now. I want inverse to be having this property. QQ inverse and Q inverse Q should be 1. So we pre and post multiply by Q star. And then each one we equated to Q star. That is Q star Q Q inverse should be Q star, or Q inverse Q Q star should be Q star. So each case, if you do it separately, what will you get? Q inverse should be, since we know that Q star Q is a scalar quantity, we can
Yes, sir.
do
Yes,
this operation. That is Q inverse is Q star divided by norm square.
yes, sir.
I derived it now actually.
Yes, sir. Yes.
Okay, so once again, go back and suppose if you have two pure quaternions R and S, and if you do a quaternion multiplication, what happens is cross product term as well as dot product term comes. So this is where that impurity is creeping in. You can show this is your quaternion multiplication. Quaternion multiplication is not simply cross product, because only for special cases like I, J, K, I cross J and I, J are equivalent. But for an ordinary quaternion R and S, that is not true. Even that impure part also creeps in. Here the multiplication is, this is the definition of your pure quaternion multiplication. Not definition, this is the interpretation by using quaternion operations. That is cross product is present as well as dot product is present in the final expression. Suppose if you want to see, we know that it is a rotation operation now. Let us see what is the matrix equivalent for that. Suppose if you are given a quaternion, how to give a corresponding DCM version for that. So for that, you have to actually expand this expression LP of Q, what was given to you, that is PQ P star, and then write it in the matrix form. It's going to be tedious, but this is the expression you will get. So if you are given quaternion, you can directly compute the DCM matrix by this complicated expression. So you can either multiply the quaternions in the way you are told, or you can multiply for rotation operation, okay, using the rotation matrices like this. So many times people usually prefer to use this matrix multiplication because in the computer it is easy to represent. There is no quaternion multiplication defined in the computer. Therefore, they would prefer to use this. So if you have already defined the modules for that, then you can directly use the quaternion multiplication. Is this okay?
Yes, sir.
Yes, sir.
If someone gives DCM matrix, how will you get the quaternion now? You have to compare with this template, that's all. And see how to extract P naught P1. How many 9 expressions are there? 9 equations are there. Actually, you require only 4 equations because 4 unknowns are there. So you combine these things in some way and obtain the result. Compute the trace, what will you get?
6p naught
Would
square
be-
minus 3 plus 2 times p1 square plus p2 square.
Yeah, something. So you remember that the trace of a DCM matrix, P naught is representing the cosine of theta, right? In the trace of the DCM matrix also that cos theta came, if you remember. So
Yes.
all
Yes,
these
sir.
are playing a role. Okay, so somehow you can extract. But however, you want other things also. So P1, P2, P3, if you have to extract, then you have to look at that. For instance, the second row, first element, first row, second element, second row, first element, second row, first element. So if you subtract one from another, you can notice that 2p1 p2 plus 2p0 p3, that is second row first element, minus 2p1 p2 minus 2p0 p3, you will get only 4 times p0 p3. Similarly, third row first element, first row third element, you can remove 2p1 p3 term. So you will get 4 times p0 p2. So only that p0 term can be retained by doing such operations, off diagonal operations. Similarly, if you subtract third row second element and second row third element, 2p2 p3 can be eliminated and 4 times p0 p1 will remain. So 4 times p0 p1, in another case it was 4 times p0 p2 and 4 times p0 p3. But p0 you computed from the diagonal elements, trace. So then you can play around and get all these elements. Okay, so that is later on you can try that out. So your rotation operation is expressed as P times Q. I think there is a typo in the last statement. It is P star QP is nothing but P transpose Q. Otherwise, the transpose comes because of star coming before. That's a typo in the last expression.
So that can't we just say that since this is the rotation matrix, P transpose is going to be the inverse rotation matrix.
Yeah, we can.
And since that represents the left hand side represents the inverse transpose, rotation, this is these two are equal.
Simple verification. Just P star, if you apply, you simply have to change these numbers. That's all here. Then you will see that that matrix becomes diagonal. You already know what is one of them, no? So everywhere P1 has to be replaced, P1, P2, P3 has to be replaced by its negation. So you can notice that P1 square is not going to change its sign. And P1, P2, any time, whenever it appears twice, it's a quadratic product, then also sign will not change. The only signs where it will change is when P1 or P2 or P3 appears individually and not in the square form. So you will notice that in the second row, first row, second element, P3 occurs. So that minus 2 P0 P3 will become plus. Similarly, first row, third element, it will become minus 2 P0 P2. So this is how you just substitute one value and show it is transpose. That's all. There isn't much actually in both the cases.
Sir, from the trace we'll get that p naught square equal to some value. Again, like we'll have both negative and a positive solution. So,
Yeah, right.
sir, we need to eliminate using other equations also.
True. We may have to use things also. One of them will give you one solution, another will give you another solution. Yes.
Okay, sir.
But trace does play some role. That's all. And okay. So quaternion product in matrix form. Let us see how quaternion product can be expressed in matrix form. We already know that if two quaternions are multiplied, we have this complicated expression. So if you take Q naught from everything and Q1 from everything, Q2, Q3 separately, then you get this matrix, first matrix above. And if you take P naught, P1, P2, P3 common, then you will get the second matrix. So either you can use this matrix multiplication, 4 cross 4 multiplying, 4 cross 4 matrix multiplying a 4 vector, or directly this complicated expression. Both are equivalent. So many times for understanding the properties, people do use these things.
So there should be IJK somewhere.
IJK?
Sir, in the matrix IJK is not present at all anywhere.
Yeah, actually we should not, what we should do, what I should have stated here is only the vector product, the PQ of not PQ of 1, PQ of 2, PQ of 3. These are representing only that scalar quantities. This is an abuse of notation, you are right. I should not write PQ, I should say vector which represents PQ will have this expression. That will be okay, right? Vector which represents the product PQ.
Sir, like, where is the vector here, sir? Like,
I have not written. I am saying that you have to imagine like that. I have abused the notation here, which is not right. So in your mind, what you can do is you can imagine that I am thinking of this as a product. After product operation, you get 4 different numbers as coefficients for PQ, right? See, finally,
okay,
quaternion is a collection of 4 numbers.
okay, sir. But
In that sense, I am saying. I got your confusion because
okay, sir.
where does this IJK goes?
Yes,
That,
sir.
that's a right question. You asked the right question, but this is the answer.
Okay, sir.
Answer is I have abused the notation. That is why this confusion is there. So try to imagine it as a vector representation of a vector product.
Okay, sir.
Okay. So then similarly, compute what is Q times P. Because these things are given, you simply have to go back and substitute the things in a way and see how the transpose or something occurs in the expression. Suppose if you take the Euler angle and Euler angle axis sequence, you have 3 sequences of rotation. So in quaternion also you can multiply that sequence. So each of the sequence of rotation is expressed by the appropriate quaternion. Cos psi by 2 plus k sin psi by 2, cos theta by 2, j sin theta by 2. Depending on which rotation is done first, you multiply these sequence in a particular way. Here we are assuming x is the first rotation, y and then z. So this is the sequence of multiplication. So when you multiply these qz, qy, qx, the matrix you are going to obtain will be this complicated expression. So q naught will turn out to be this one, q1, q2, and q3 in terms of Euler angles and Euler angles for the classical sequence, XYZ rotation. So if Euler angles and classical sequence is given, The corresponding quaternion is given by these four expressions.
Sir?
Yeah.
Sir, for aerospace applications, classical Euler sequence, you said that it was ZX, Z, right, sir? So here it is given Z.
Tell me again, the classical sequences?
ZX, Z, no, sir.
Is it ulta? Okay, so then you have to
No, sir,
multiply.
like,
You said okay. Sorry, this is not classical sequence then. It is the aerospace sequence. Yes, you are right. Got it. Classic. There are two things: ZXZ and ZXY, or whichever it is. Yeah. Thanks. That's right. And then the other one, if the DCM components are given by this expression, this was what we discussed in the beginning. From the DCM matrix, how to compute the P0, P1, P2 square. So the alternate expression is given in the second row. So you, this is the quaternion we have to extract. No, this is the other one. This is how to compute the direction cosines. I think this we already know. Once you know the quaternion, this one, so the axis of rotation is known, the angle is known. So then it is not difficult to compute. Once the quaternion is known, you compute the DCM matrix in this particular fashion. And you can also compute the direction cosines of the axis and the angles are known. This is the other one. Suppose if P1, P2, P3, those things are known, how to, if the direction cosine and the, we had derived one expression, if you remember that complicated expression, that axis and angle are known, then how to compute the rotation matrix. I think the same thing is appearing here again. This we already know. You don't have to worry about this. Quaternion to direction cosine is this expression. It's obvious. We have already seen that. Then quaternion to Euler angle and Euler axis, you have to do that comparison. So once you have that, I think this is once you have the DCM matrix, from the DCM matrix, you can compute these location expressions. So similarly, if quaternion is given, you go to DCM matrix and then the Euler angles. Or you may have to work with this complicated expression here. This is too much, but yeah. The process which is shown here is you are given quaternion. So go to a DCM matrix. DCM matrix will have these complicated expressions. And then from DCM matrix, come back to the Euler sequences, Euler angles and Euler sequences, corresponding to the whichever sequence you are using, that particular template you have to compare. There are many such things you have to compare appropriate template. There is quaternion to Euler angles via DCM matrix. Otherwise, you have to use these things, which is not easy to manipulate. Okay, so in one or two more conversions only. So direction cosines to quaternions, this is what we were explaining. So you compute this 4P0 P1, 4P0 P2, and 4P0 P3. That is off diagonal elements. If you subtract, then you can see everything has one common thing, which is P0. If you compute trace of this quantity and P0 P thing is 1, you will get P0 is equals to half of this expression. So one of your exercise will be, later on we will come to that. That is, what is the angle represented, what is the axis and angle represented by minus cos theta minus u sin theta. Okay, so later on we will look at that. So that is where you can actually eliminate one of the negative values here. That is the clue for this particular trace computation, why the positive value of P naught is enough. I will not tell you, you can go back and work on that. Later on in the next class, we will discuss that. So P1 obviously is divided by this off diagonal difference divided by 4 P naught, similarly all things. So what is the catch here? If P naught is 0, what will you do? This computation will not hold. So you have to use some other elimination mechanism. So this elimination mechanism holds good only when P naught is non-zero. So you have to use alternate expansion eliminations depending on whether P naught is 0 or not. The disadvantage is this procedure fails. Sorry, not Q naught. There is one more typo here. If P naught is 0. Okay, I know that too many things are there, but they are only converting from one to another. If you know something, you can go back. So we will briefly mention this particular method which was discussed in this article in 2000. So if you have to compute the quaternion and you are given only the DCM matrix, they had suggested this particular method. For the proof, you have to go to this article. So what does it say? You construct a 4 cross 4 matrix from the 3 cross 3 matrix, which is your DCM matrix, and compute the eigenvalue, a vector corresponding to eigenvalue 1. So that eigenvector will represent the quaternion under consideration. I am not going to prove it. This is just for your mentioning. So basically, eigenvector corresponding to eigenvalue 1 is your desired quaternion. Is the statement clear? I am not proving anything here. You are given a DCM matrix. From the DCM matrix, compute the 4 cross 4 matrix which is shown here. And for this 4 cross 4 matrix, compute the eigenvalue equals to 1. And the compute the eigenvector corresponding to eigenvalue equals to 1. So that eigenvector will represent the quaternion corresponding to the DCM matrix under consideration.
So this
So
will
the
represent.
example, yeah,
Q is a DCM matrix, right? Given.
yeah, Q11, Q12, Q33, they are all your components of the DCM matrix.
Yes.
And then you are combining the components of the DCM matrix for each component of the 4 cross 4 matrix given here, K. And for this complicated K matrix, you compute the eigenvector corresponding to eigenvalue 1. So the example is this particular one.
Sir,
From the Q matrix, you get this K matrix. So given matrix is Q, you obtain K. How will you obtain K? Using this expression. So first component, at least you can try whether this is right. Using this expression, Q11 is minus 0.545, minus Q22 is minus 0.603, minus Q33. So it is plus 913. If you compute that, I hope you will get minus 0.574. Do you get that?
So during exam, how will we calculate such large matrices? Sir?
We will see. I will not give all these complicated things. Don't worry.
sir, it is not.
Okay, sir.
It is not.
I don't like mine. The answer is coming different for me.
Even for me.
Not correct, is it? Okay, so then I think go to this article and then check. I have taken these things from there. Okay, just
Okay, sir.
verify it. So Q11 minus Q22 minus Q33. You are not getting this one. Are you sure?
Yes, sir. It will be around minus 0.2, I think.
Is it? Okay. So then I think that's a mistake either in my computation or have I taken it from the article directly? I do not know. Okay, I will check it out. Just send me one mail reminding that. I will also share that article with you. Yeah, but if effectively, that's what we have to do. And then if you compute the eigenvector corresponding to eigenvalue 1 for this particular matrix, which I will go back and verify now, you will get this expression. If you convert to this expression to norm 1, then you will get the corresponding eigenvector. But unfortunately, what happens is the numbers will have errors. So Q11, Q22, Q33, they are not very precise. So usually you will never be able to find out an eigenvalue for this matrix which is equal to 1. So this usually happens because of numerical errors. What we have to do, this is called non-orthogonal because of the errors. The matrices will not be orthogonal. So in that particular case, instead of computing the eigenvector corresponding to eigenvalue 1, you compute the eigenvector corresponding to largest eigenvalue, that is the lambda max. So the eigenvector x max corresponding to lambda max is the desired quaternion. The same matrix, okay, nothing has changed. Okay, so that's all I wanted to talk to you about today. Okay. From the next class, we will do, I think tomorrow there is no class, right?
No, sir.
14th, we don't have classes.
Sir, I couldn't understand why you are taking this largest eigenvalue. What is the problem with 1?
Problem is now matrix due to numerical errors. We will later on see that this matrix is however this matrix is computed, we have to see. In an ideal situation, this matrix will have the orthonormal properties and all. So when this matrix is not orthonormal, this 4 cross 4 matrix what you have computed will not have an eigenvalue equal to 1. So then how will you compute the eigenvector?
Okay, sir.
Okay, so therefore you look at the largest eigenvalue. There are actually techniques to compute matrix techniques to compute largest eigenvalues. There are easier techniques. So therefore this is actually comes into the numerical computational area. So I'm just mentioning them matrix computations. If you go and look how to compute the largest eigenvalue, they will talk to you about that. Or eigenvector corresponding to largest eigenvalue, how to compute that. If you look at it, you will get some idea. So what happens, you have to imagine like that, like this. So assume that you have an arbitrary matrix. An arbitrary matrix will have so many eigenvalues and so many eigenvectors. And then there will, let us assume that there is a largest eigenvalue. So when you multiply any arbitrary vector with this matrix, what will happen? The resulting expression will be some linear combinations of these eigenvectors, right? Okay, so let me explain that for a 2 cross 2. This is an interesting thing which may help you in some other cases. So let us take example. I wouldn't say numerical example. Let there be a matrix, 2 cross 2 matrix. Let V1, V2 be eigenvectors corresponding to alpha 1, alpha 2 belonging to R. Do you accept this statement? Not proof, we are assuming.
Yes, sir.
Okay, sir.
Let V B arbitrary vector in R2. So, sorry, this V, since this eigen alpha 1 and alpha 2 are distinct, so therefore V1 and V2 are also linearly independent. Okay. So this implies we are assuming that V1, because of these things, V1 and V2 are linearly independent. Is this okay?
Yes, sir.
Yes, sir.
So this implies V equals to some V1, V2. No, I should not put suffix. I will put superscripts, because usually suffixes are used for A times V1 plus B times V2. Do you agree?
Yes, sir.
They form a basis. They are linearly independent. So what happens to QV? Consider. So this will becomes QAV1 plus BV2. So this is equals to A times QV1, B times QV2. But this is equal to A alpha
0.
1 V1, B alpha 2 V2. Right?
Yes, sir.
What is
Yes.
2 times QV or Q square V? A times alpha 1 square V1,
Plus
B times alpha 2 square V2.
V2.
Right?
Yes.
So QN V,
Alpha n 1 b alpha 2.
so alpha 1 greater than alpha 2 implies there exists n such that alpha 1 n is very much greater than alpha 2 n.
Yes, sir.
Of course, you have to assume the other thing also, no? Can we make this
If
assumption?
both are fractional, then we can't say.
They should be greater than 1, we have to assume, right?
Yes, sir.
That is one more assumption. Alpha 1, alpha 2. I will do this. Then at least if 1 is 1, other will be greater than 1. Then this property will hold. Even otherwise, will it hold? 0.9 square and 0.8 square if we do, which will reach 0 fast. That is one. Okay, anyway, you look at this one. Let us make a much more restrictive case. So this means, what does this mean? After some time, in your computer, you will not have place to represent this number at all. Most of the number thing will be swallowed by this one.
Yes, sir.
So you are indirectly computing Qn will become
A into alpha 1.
is very close to V1 axis.
Yes, sir.
Yes. So that is why that largest eigenvector computation is not a difficult task.
Sir, then we need to make a Qn for that, right? Like the two metric.
Yeah, you have to keep on computing the same thing. Otherwise, eigenvector computation is you have that there may be no direct polynomials to do that. No, you have that difficulty. See, what happens is, of course, this is a 4 cross 4 matrix. It is okay here. If it is 5 cross 5 or above, you will end up with a suppose. Okay, so this case, what your statement is right. We can directly compute the eigenvalues and then do it, because the eigenvalue polynomial is of the order 4. So direct formulas exist for computing the direct formulas exist. Just a moment. So therefore, direct formulas exist for computing for order 4 or less polynomials. So you imagine a situation, you have a polynomial of order 5. So can you compute the roots of the polynomial of order 5 or greater directly? Do you have formulas to compute roots for order 5 or more?
No, sir.
There exists no formula actually. So because of that, if you cannot compute it directly, you will have iterative algorithms to compute the roots of polynomials greater than degree 5. So only after computing the eigenvalues in this iterative fashion, you will go to compute the eigenvectors. So instead of that, this method directly gives you a mechanism to compute the eigenvector in a straightforward fashion, corresponding to only largest eigenvalue. Okay, only this case. Yeah, this was the idea why they came up with for this particular thing, largest eigenvalue. Okay, but why that this should be in the direction of quaternion? These proofs are given in this book. Sorry, not book, article. This article you have to go back and refer. Okay, any other questions? The class is over, so if you have questions, we can discuss about it. You can stop recording also.
Recording stopped.
No questions.
Okay, have a good day, everyone. Thank you for coming.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.